So there's an SI session tonight from 7:30 to 9:30 in Rock 301, and you should come.
And Jess just ate chalk for $1.
All right,
It looked
there's
really
two more
gross.
announcements.
Okay. Hi, everyone. My name is Prasanthi Paritala, and I'm the president of Students for Organ Donation Awareness. I just wanted to make a quick announcement about an event that we're hosting tomorrow. It's a speaker event. It's going to be in Nord 310 from 11:30 to 1. That's during Provost Hour. And there will be free food from Aladdin's. To tell you a little bit about the speaker, his name is Michael Yeager. He's a resident nurse at Cleveland Clinic in the cardiovascular surgery department. And he's going to be talking about mechanical circulatory support. And I don't know if you've heard of that before, but it involves some implantable devices that surgeons can implant into someone's circulatory system, and they help them buy time for patients who are waiting for heart transplants. It gives them a little bit more time to wait on the list because obviously there are a lot of people waiting to receive heart transplants, and with a lack of organ donors, which is why we're hosting this event. So please, if you have time and you would like to listen to the speaker, come down to Nord 310. And we'll also be having tables all week in Nord with information about organ donation registry. And we'll be selling these bracelets for $1. And all of the proceeds go to Donate Life, which is an organization that helps families of people who've received donation transplants and helps cover costs of transplant surgeries as well. Okay, so we hope to see you tomorrow. Thank you.
I think there's one more. I need a bracelet. I'll be over there.
Hi, my name is Jordan Foley. This is a class officer announcement. It's time for Hudson Relays, so we're assembling a team of people that can run and run well. If you're not familiar with it, it's a 26-mile race, and each member of the team runs a half mile. And right now, we're looking to beat everybody this year, and if you win 4 years in a row, the entire class gets a steak dinner, so we're trying to start off with a win. Time trials will be held tomorrow at the NRV field at 7 p.m., so if you have any questions, just email me or get in touch with me via Facebook. But we're just going to have people show up tomorrow at 7 and just write down some times and get the best team possible, and I believe extra credit will be offered in chem. We haven't discussed the logistics, but we will write your name down. If you make the team or not, you will get extra credit. And you can also get extra credit in any math class taught by Peter Garfield or Chris Butler. So get some chances for double extra credit. But again, that's 7 o'clock tomorrow, NRV track. Thank you.
You're going to take attendance for me?
Yeah, definitely.
And times?
And times.
All right.
You want times too?
I want times too. Heck, I want times. All right, here's the deal on bonus. First of all, anyone who tries out for the Hudson Relay will get a bonus point. I had people last year who showed up at the track and walked the half mile for their bonus point. They didn't even, yeah, I would like to see them make a lap around the track, Taylor, okay? So if you go and you try out for the team, you will get a bonus point, and as you just learned, you'll also get a bonus point in your math class. Chris Butler is the first-year student team coach, so he always gives a bonus, and Peter Garfield supports it. I also support it. The other deal that I made last year was anybody who could beat me could get 3 bonus points. Last year it took a 2:05 to beat me for a half mile. I haven't run in a year, so I'm not offering that opportunity this year. One person I did give 3 bonus points to last year because he ran a 1:59 half. I'll come to that. So the Hudson Relays is one. Please do consider trying out for that. It's at the new residential village. It's the new track, the football field, so show up there tomorrow night. So that you know, by the way, last year, the first-year class and the second-year class, so this year's second and third-year classes, both beat the course record. I mean, they blew it away. The course record by about 10 minutes. And so there's bragging rights on the line now. So there is stiff competition. The seniors last year were quite adamant that they would win. They finished 4th. The last year's first-year class filed an appeal because the second-year class appeared to take a shortcut at one point. It was disputed, and in the end, it was not resolved. So last year's first-year class, your class ahead of you, has a chip on their shoulder at the moment. So it would be a good, it's a lot of fun. The race itself is the Saturday of Springfest. So what is that, Saturday the 27th? I'm sorry? 26th? It takes place in the morning. You only have to run a half mile, and if you get the elephant stairs for your shift, if you happen to draw the elephant stairs or volunteer for it, I'll double your bonus. So to anybody who's willing to run that stairs, that is one half-mile segment, by the way. I strongly encourage you to do it. It's a lot of fun. Second, any seminar, any 2 seminars between now and the end of the semester, your choice. You may attend and write a reflection on, and that will be bonus opportunities. I will be posting all these to Blackboard, so they'll all be summarized. 1 point for each one, so you can earn up to 2 bonus points. So any 2 seminars. Let's see. I'd love to say the baseball game, but that's only if it happened at 3 o'clock on a Monday, Wednesday, Friday would I do that. That way we could all go to the baseball game. You still get a bonus if you donate blood, and if you can't donate blood or choose not to, you can do community service in its place. You can do that up to twice. Let's see, what else did I have? We have the Chem Fiesta on Sunday. Whatever the last Sunday in April is, that will be a bonus opportunity for you. There was a couple of others that we came up with. As I said, I'll summarize them on Blackboard. If you can't donate blood, if you volunteer, that's fine. Oh, you still owe me for that. You have to let me know you did that. The resonance blood drive of a couple of weeks ago, I said if you bought a shirt, you could do that. But you can't get the blood donation and the shirt donation and the volunteering for that. It's one of the 3. You only get 1 point for the resonance activities for those who did that. Was there a question over this way? Nope, okay. I think I did get an email on the resonance who did all the stuff for resonance, okay? Yeah, they wrote all that down. So I have all that. I have to get it up to Blackboard for you. Okay? Other questions? Here's go ahead. No. Oh, it is a seminar, yeah. Any 2 seminars between now and the end of the semester. Yeah, the one tomorrow. So I'm not singling any out. There's some very good ones between now and the end of the semester, that being one of them. Here's the other one you'll like, perhaps. I don't want to write the final exam, so I'm going to let you write it. Anyone who authors a final exam question and an answer, you have to write a question and the answer that goes with it. Posts it to the discussion board for all to see. And I will pull all the final exam questions from there if there are sufficient numbers of them. What's sufficient numbers? I don't know yet. But if I have a large enough data bank of questions, and I will tell you a week in advance of the final exam, so between now and a week before the final exam, you can author a final exam question. And you need to put a little bit of thought into it. Don't just take a problem from the book and say, here's a good final exam question. I won't accept that. If you create a final exam question that I could potentially use, and you put the answer up, because I want to see the people, do you have to get the answer right? No. But hopefully if it's wrong, somebody will start a discussion that says, wait a second, you forgot to multiply by 2. So it's a place for you to review. Are you going to use the same numbers? Yeah, I would use the questions that are up there. So if you want to memorize every question that's on the discussion board, that's fine with me. Remember, it is cumulative for the year, which doesn't mean, okay, I'm going to take this question from chapter 6. What it means is, okay, if I want to calculate the pH of a solution, and I tell you I dissolved 48 grams of nitric acid in 500 milliliters of water, A, you got to know how to calculate molar mass of nitric acid. B, you need to know how to calculate molarity. That's cumulative in my mind. It's not, okay, in chapter 6 we talked about Vesper theory, and you could figure out what the structure of this molecule is. That's okay. It's not a great question. If it's part of a longer question, that's good. So think creatively. Think about it a little bit. Post things up there. I will provide feedback as well. So if I say, hey, this is a really cool question, that's a good hint. You can write as many as you want, but you will only get, let me think about it. I mean, someone could go up there and write 10 questions and say, okay, I did 10 questions, there's 10 bonus points. No, I don't want to do that. I want you to, the idea is you spread it around a bit. The last bonus opportunity I can share with you is, I think it's next Friday. Oh, that was the other thing. Yeah, I give you you get 1 point for writing a question, you get a second point if I use it. So if I use your question, and I will not identify you by name on the exam, I will know whose I use. Then it's a second point. Thank you. That was what I did last year. When is jail? Do you know? AP, anybody in Alpha Phi Omega here? When is jail? Next Friday? So 2 weeks from Friday? August 28th. No, not August 28th. April 28th? That makes sense. Am I slated? All right. There's a fundraiser. Actually, where's the dental people? They wanted me to do one too. Is the dental, anybody from the dental student club here? I will post that one for you. That's next Thursday. They're looking for dental supplies donation. So it's one more donation opportunity for you. Toothbrushes, floss, toothpaste, mouthwash, that kind of stuff. I'll post it to Blackboard. No, the other one is APO, Alpha Phi Omega, is doing a fundraiser. Where's the money going? Oh, that's right. Whatever, certain faculty will be asked to sit in jail. It is a Friday afternoon. It's the last Friday of the semester. It's out on the quad. I've been asked to sit in jail. I've said I'm free from 11:30 to 2. And I'll throw it out to you. Here's two options for you to consider. I don't want you to buy bonus points, quite honestly. However, why should I stop now, right? However, here's two options for you to consider. One of them is that for every $100 raised, I will stay in jail an additional 10 minutes. So that means that if I'm there at 2 o'clock and there's $100, I won't leave jail till 2:10. If you raise $500, it means there's no class that Friday. Okay? The jail, I'm going to be locked into an area on the quad and I won't be able to get out until I raise bail. And bail is raised by making donations. But you can also pay to keep someone in jail. So that's option one. $100 in my name, and for every $100 contributed in my name, I would stay in jail an additional 10 minutes. The second option is, for every $100 raised in my name, I will grant 1 bonus point to every student in the class. So if you do the calculation, that means with 250 students in this class, for $4 from everybody, you all get 10 bonus points. So, or from any one person, $1,000 and everybody gets 10 bonus points. Anyway, so you can either pay to keep me in jail or you can pay to get me out. I'll take whichever one raises the most money to tell me what people really think of me. What? Yeah, would I combine them? Well, that's what I'm just trying to decide. What if I don't combine them? Then we raise $2,000 or $1,500.
So if the money goes towards getting you out, that's when we get the bonus points?
I have to think about how to do that if you keep me in jail or if you bail me out or keep me in. So I'm thinking about how to do it. If you are violently opposed to either of those on moral, ethical, or other grounds, please talk to me. All right? You are?
We didn't get to buy our bonus points.
Oh, of course not. I didn't like you as much. I'm just kidding, Jess. You know that. All right. Huh? You ate chalk for me. All right. Question. If you have still are unable to do the PDF, just email me the scores. Okay? Yeah, if you still haven't got the PDF to work, email me the scores. It ends up there, it's proving to be a little more challenging than we thought anyway, so. All right. Back to electrochemistry. The whys, the what's important to you kind of things. Thanks, Amelia. Yeah. Try the other one. Wrong one. Just throw them all up and turn them on one at a time. Eventually, there we go. All right, a car battery. The main thing about these, and we gave you this yesterday. You can actually read that, can't you? I can blow it up if you need me to. Lead ions plus sulfate ions to give you lead sulfate is one half cell, and the other half cell is the lead oxide plus sulfuric acid to give you lead sulfate and water. When you combine the two half cells together, the two half reactions, you get the overall reaction where lead is reacting with lead oxide in the presence of sulfuric acid. There are 6 of these cells where a cell is one reaction lined up in series, and so you get a total of 12 volts out of this. Some of the beauties of the benefits of this kind of cell, or this kind of battery, the main one is that it generates a high current for a short period of time. Cell potential, the voltage difference between the left-hand side of the reaction and the right-hand side of the reaction, doesn't depend upon what you've got. Or excuse me, doesn't depend upon how much you've got, it depends upon what's in there. Just like if you make a buffer, it doesn't matter if I've got 1 liter of each, the acid and its conjugate base, or I start with 10 liters, or I start with a tank car full. What matters is the concentration. In a battery, or in an electrochemical cell, once you've identified the two half reactions, you've set the cell potential between them. And it's theoretical that it is going to change. It goes down as a function of time because you're using up reactants and making products. But this one generates a high current, and the reason why, where current is the number of electrons that are transferred, is because of the way it's designed. You've got lead plates interspersed between the lead oxide plates. And the lead oxide plates is really just a wire mesh that's coated with this lead oxide paste. And so you've got a sheet of lead and a sheet of lead oxide, and they're sandwiched together so that they intersperse between each other. And there's sulfuric acid in this, and it's concentrated sulfuric acid. Having worked at Sears in an earlier life and carried more batteries than I care to admit, and have the lead acid holes to prove it, this is messy stuff. But because you have all that metal in there and all that surface area, you get a huge flow of electrons. And for starting a car, that's what you need. One of the problems with this thing, though, is that it's very heavy. A lead storage battery has lead plate in it, so it weighs, each car battery weighs about 15, 16 pounds. They're not lightweight. And as we move to electrical systems in our cars, in about 3 years, the electrical system in your car is going to go from a 12-volt system to a 43-volt system. 42-volt, excuse me. So all of a sudden, we're going to have to go from 1 car battery to 3.5 car batteries in every single vehicle. Now, the reason why they're doing that is because they're changing the way your car is going to run. Right now, when you turn your steering wheel, you turn a cable on a pulley that turns on a shaft that goes down to a gear. That gear turns and then splits, and it turns your wheels so that the wheels turn. There's a lot of weight involved in those gears and those pulleys and a lot of friction. After charge? It says where? Right here? It says charge? Oh, I'm getting to that. It says green eye. Yeah, I'll get to that one. What they're going to do with your car, and they've already started on some cars, the Cadillac STS has it, most of the top-end Lexus have them, some of the Acuras have them, is they're going to go to something called steering by wire. They're going to take out all the rods and gears that go from the steering wheel to the wheels, and they're going to replace it with a single wire. So what you're going to do is you're going to turn your car wheel, and it's going to be a switch. And it will sense where you are, and it'll send an electrical signal from the wheel of your car, steering wheel of your car, to the wheels and tell them to turn. And so we've eliminated all this metal gearing that's in there, and you've cut down the weight. As soon as you cut down the weight, you increase the gas mileage without doing anything else to it. Well, that's great. They also want to do it for another major mechanical system in your car that weighs quite a bit, your brakes. Right now, when you press on the brake pedal, you're squeezing a piston that's filled with hydraulic fluid. That's compressing the fluid in the brake line. The brake line is compressing another piston on a caliper that's squeezing down on the brake on your tire, and it's slowing you down. If you think about it, that's all made out of iron. Every piece of that hydraulic system is a piece of iron, other than the brake lines, which are nice copper lines. And we're going to replace all of that and replace it with a single wire. So now when you press your brake, you're not compressing a piston anymore. You're pushing a switch. And the biggest concern the engineers first had was, when you press that switch, right now when you press the brake, you can feel it. You know that you've stomped on the brakes. And they wanted to keep that sensation there because people need to know they're actually if you've ever been in a quick stop situation, you know, you sit there and you slam on that brake. You want to know that you've pressed it. And if it ever goes straight to the floor with no resistance, then you worry. Well, think about it. Now you've got a switch in there that you're pushing on. Well, that's easy. You just push down and it stops. So they had to put a feedback loop in it that drives an electrical motor that pushes back against you. And as you push harder, it pushes harder against you. So it makes it seem like you're pushing against a brake again. But really, there's just now a little wire that goes from the brake pedal to the brake caliper, and it closes the brake. And everybody says, hey, that's great, except what happens when that wire breaks? Hopefully there's redundancy built into it. You want to control it, and so that feedback loop that they've put into it, the electrical feedback, allows you to get that tactile sensation that says, okay, I'm slowing the car down gradually instead of coming to a very quick stop.
I was going to ask the same question, like, does it do it gradually, like, without how much pressure you're putting on it, if that's how much pressure it can apply?
One of the biggest selling points of the first new car I ever bought in the mid-'80s was Honda came out with what they called variable assist power steering. If you've ever driven a car that did not have power steering, you sit there and you work really hard to turn the wheels unless you're moving at very high speeds. At very high speeds, you've got a very nice feel, it feels great. Well, what Honda did was they said, hey, let's take the benefits of high-speed steering and make it easier to parallel park. Think about parallel parking without power steering. Right now, you just do this and this. You pull into the spot, you're done. Without that, you crank the wheel, and you crank it the other way. And so variable assist power steering was, at low speeds, you have power steering, and at high speeds, you don't, so you get a better feel for the road. They're going to do the same thing with braking. Variable assist braking, so it feels, you can sense it. But they're doing it all electronically now, and they calculated they get rid of about 20% of the weight. But because now you have these additional electrical systems, you're up to 42 volts. Well, if you've got 42 volts and you need 3.5 car batteries, sure, I've taken out all this weight, but now I put these lead storage batteries in. When Honda made their first electric hybrid, it was an ugly-looking car. There's a reason why the Prius made it and the Honda version did not. The Honda version had 10 lead-acid batteries in it. It was all in the back end. Believe me, it did not work well in snow. Because even though the engine was in the front end, and the benefit of front-wheel drive and avoiding skidding is because the weight's on the front wheel, so when you steer, you're not going to slide. If the weight's on the back, the wheels lift up just a little bit. Guess what? Those 10 batteries in the back were enough to make it so this car was not real good in the winter. But you also had all this, and it took up all this space, and everybody's thinking, I have all that sulfuric acid in the back of my car. It did not sell well. They quit making it after about 4 years. You can still see a few of them running around, but there's not many. The Prius, on the other hand, has done great. And the Prius, Toyota has not been very forthcoming in how they do what they do. So the US government bought 2 Toyota Priuses. They're in Oak Ridge, Tennessee. One of them is completely disassembled, nuts, bolts, washers all over the floor of the lab. This is one of the places I visited a few years ago. And the other one is perfect still. And so they've torn this thing apart, and they have the black box. And the black box is how they convert braking power into recharging power of the battery. And they can't figure out how it works yet. The Toyota engineers did a phenomenal job. They're tearing that apart too to figure it out. They're reverse engineering the whole thing. And who's paying for it? Not you and me. The car companies are funding it. So GM and Ford, and they're all paying for it. Another benefit of this battery is that it's rechargeable, as we already talked about. As you're driving down the road, the alternator is converting alternating current into direct current and recharging the battery. One of the other benefits of this battery is, again, if you talk to your grandparents probably, maybe your parents, they'll remember how when you used to go to a gas station and someone actually came out to your car and filled it for you, they'd check your tire and your battery pressure and the water in your radiator, and they'd check your battery. And what they do is they pull the cap off the battery, and those of you who have boats probably still do this. You draw out some of the liquid that's in there, and you tip it upside down, and there's different colored beads inside there, and you see which bead is floating. And it tells you the density of the liquid that's in there. Well, if you look at this reaction, here's the sulfuric acid. The density of sulfuric acid is much greater than the density of water. If the car battery is discharged significantly, there's not much sulfuric acid. It's all converted to water. And so if you measure the density of the liquid that's inside the battery, you can find out if it's sulfuric acid or water, and it's some number between 1.0 and 1.2, and whatever it is, it's just a linear extrapolation. You can tell, is it 50% charged, is it 25% charged, or what? Nowadays, they don't have batteries with these refillable cells. They're all sealed. And instead, hopefully you've all learned, that when you pick up the hood, you take your finger, you brush off the dust, and you look and see if the eye in the battery is green or not. If it's green, the battery's okay. If it's yellow, it's not a good thing. If it's red, you're in trouble. Well, how does it get green? It measures the density of the sulfuric acid, of the liquid that's in the battery. And as long as the density is close enough to sulfuric acid, it stays green. It changes color when the density goes down. And so if you look in there and see a yellow one, you should start to be concerned. Like I said, if it's red, go get a new battery. It will not last much longer. The other one, and this is a trick we learned, I grew up in Minnesota, and for your 16th birthday, everybody gets the same thing in Minnesota. Jumper cables. You will need to jump your car at some point in the wintertime. In the wintertime, it's much harder to start the car. And it's not because the electrons don't flow very easily, because yes, they do, the temperature does affect the ability to generate current, but it's because the liquid that's in the battery, it doesn't freeze. It's a very concentrated sulfuric acid solution, and we all know that the freezing point goes down for electrolyte solution. So it's not that the solution freezes, but it does become more viscous. And so it doesn't flow very easily. And if it doesn't move, then the reaction doesn't happen, and then it does slow down the amount of current you get flowing through the battery. So what the advice has always been, and again, we learned this in driver's ed, you unscrew the two connections on the battery, you pick it up, you take it in the house overnight, let it warm up, and then put it back in the car in the morning, and everything will be just fine because you kept the battery warm. And it works. You don't have to hook it up to a charger, you just have to keep it warm. So they're all back to the chemistry of what's going on in this thing. This one's the D battery. D was a size. It actually stood for dry cell. It's also, the original one's called the Leclanche cell. And up in the upper left here, you can see what it first looked like. There's a solution of ammonium chloride surrounding a zinc electrode. This is a carbon electrode here. It's just a piece of graphite. Over here, this porous earthen pot, that's the salt bridge. And inside of there, there's manganese dioxide and granulated carbon. Well, here's the reaction that's happening. Zinc solid is forming zinc ions. Zinc's a very cheap metal, so it gets used a lot. In the powdered manganese dioxide, we have some ammonium ions, some manganese dioxide. We're going to make manganese trioxide, ammonia, and water. And when you combine these two half cells together, you get 1.5 volts. And the net reaction, you can just add them together, is pretty straightforward. You could tell when a D cell, an original D cell, an ever-ready battery was bad because it smelled like ammonia. The other thing was they would bulge quite frequently. When you generated the ammonia, some of it would convert to gas, and so you'd get this bulging in there, which was ammonia gas. And if you ever broke that, it really stunk. Well, this is a new picture, a newer picture of that same battery. You can see they've improved the engineering a little bit. Let me blow it up. It's the exact same thing in that we've got manganese dioxide and carbon. We've got where'd it go? This is a graphite carbon electrode running down the middle. The zinc is now wrapped around this thing, encasing the whole thing. And so we've got everything we need. Here we've got the manganese dioxide and the ammonium chloride. We've got the carbon electrode. Everything we need is right there. We've just improved the package a little bit. By improving the package, we make it so they don't leak so much. The ammonia doesn't diffuse out. You don't smell them when they go bad. When you put the, okay. I'll show you that. Here you can see they've improved it just a little bit more. We're taking advantage of technology. Now we've got a gel in here, which is powdered zinc. We've got, here we still have manganese dioxide and carbon. Now there's a brass rivet on the bottom, and there's a brass current collector. You can have any electrode in there you want, as long as there's something to the reaction. We still have to have some zinc in here. Where'd they hide the zinc? I can't find it. Oh, there it is. It's right there. I started with it, didn't I? Zinc, manganese dioxide, everything we need is right there. These batteries, I mean, they stopped making these. You can, I guess I take that back. You can buy these now, but they're much harder to find. One of the complaints I have now about this book is that they haven't said anything at all in the book about alkaline batteries. And I'll tell you how your question there in a second. The alkaline battery looks very similar. It still uses zinc. It still uses manganese dioxide. You still make zinc ions, except now it's zinc oxide, and you make Mn2O3. But now it's in the presence of base. And when you add the base to it, that's the net reaction. Everything's solid. So the nice thing about this battery, first of all, the really convenient thing about this battery is it has exactly the same voltage. So all of those devices that required 1.5 volts of potential to work will still work. They haven't changed that. It fits in the same size package as before. Everything's nice, but even better, the fact that these are all solid instead of being ionic solutions means it's going to last longer. In about 1985, 1990, somewhere around there, they started to freshness date batteries. All of a sudden they put these dates on it. Good until, I just opened a package that said good until 2013 and put them in the smoke detector. None of them work, so you can't believe the freshness dates. But the question is, what did they do different that in 1985 they decided they could start dating these things? The answer is nothing. Battery companies have known for years how long their batteries would likely last. They just decided to market it. So everybody said, oh, I'm going to start buying the batteries that have freshness dates on them, but there was nothing different about them. They paid a little bit more because it looked like they would last longer, but it was pure marketing. And you can do the calculation, and we'll talk about the kinetics of how you figure out how long it'll last. But there's nothing else to it. But the other thing about this thing that's nice is that now it's rechargeable. You can recharge an alkaline battery. All you have to do is take the battery, stick it into the recharger. Well, if I want to recharge it, I just have to drive the reaction back the other way. If it's a downhill in energy process to go forward, it's uphill in energy to go the other way. How do I do that? I plug it into the wall socket and I take the current from the wall and use it to force the reaction back the other direction. And since it's all solids, it works out very conveniently. You can't do it with the dry cell because the ammonia that's in there, as soon as you start to put current in there and it heats up, what do you think happens to that ammonia? It vaporizes. When it vaporizes, you get bulging, and then all of a sudden it bursts, and you've got ammonia being sprayed all over. You cannot recharge one of those, at least not safely. Chemically, it's not a problem, but you will cause problems. So you can recharge this battery, but there's a limit to how much you can recharge it, because the other thing that happens is once you convert the hydroxide ion into water, yes, you can go back the other way, but the hydroxide then limits things, the alkaline part of this. Again, you don't want to recharge it because if it did heat up and burst, you'd have hydroxide all over the place, and that would probably be worse than the ammonia. Now, you asked how do those little testers work. A 9-volt battery is exactly the same as these, by the way. It's just you have 4 of them strung together, and they're in smaller packages. And so 4, 1.5, or is it 4? Yeah, 4 times 1.5? No, 6 times 1.5. It's 6 of them strung together to get 9 volts. When you push down on those tabs to see how your battery's working, all you're doing is you're allowing current to flow through, and you're getting a chemical change in the color to see whether or not there's still current. It measures the amount of current. And if it's high enough, then it says that a battery's good. Again, it's a great piece of marketing. What about the batteries that power iPods? Back to this one for a second. The only difference between a AAA battery, a AA battery, a C-cell battery, there actually is A batteries too, by the way. There are B batteries, you don't find them very often, and D batteries, is how much material is in them. A D battery generates 1.5 volts of potential. A AAA battery generates 1.5 volts of potential. But because you have more stuff in the D battery, it will generate more current flowing through it. There's more stuff, so you generate more moles of electrons. Electrons are the current, and so the bigger the battery, the more current you get. And so that's why you have the different sizes. And if you think about how they're used, a radio usually uses the larger batteries, although now they're getting more and more efficient, they can use the smaller batteries. What if you need to have something like a completely rechargeable, very efficient battery? The nickel cadmium battery. This is like what's in your calculators.
Why would you want more current if you had the same amount of voltage as voltage?
Why would you want more current if you have the same amount of voltage? The current, the moles of electrons, is just like in a chemical reaction. The more you've got, the more product you can make. And so if the product you're looking for is energy, then you want a high current. Potential difference is the amount of potential energy you have, where the current is the actual amount of energy. So if you want a huge energy flow, you need a high current. But the potential difference is related to concentrations in what you've got. So voltage doesn't determine what it will do, current does. Okay? In a Nicad battery, again, it's a nice simple battery. It's expensive, but why do you go to something like this? Because you can get these in very small packages, and the only thing that's in here is a pressed powder negative electrode and a pressed powder positive electrode. And I like how they describe it, a jelly roll. They're just rolled together in this, and you've got all solid materials again. You've got nickel and cadmium. And because they're all solid materials, you can make these very small. They do generate a little bit of pressure, a little bit of gas can be generated in these because there is an electrolyte in there, so there's water, so if they heat up, that water may vaporize, and so they have to vent off the water, the steam that's in there. But these are very rechargeable, again, because they're all solid materials. The metals are relatively easy to get. You don't need very much because you don't need a lot of current to drive the LED in your calculator. Okay? But you are going to do it. Your question was the iPods. Lithium-ion batteries. cameras, computers, digital devices of most kinds use a lithium-ion battery. The lithium-ion battery has been looked for some time. It's only been around for a little while, and it's only become commonly available for even shorter time. You all know lithium is in the upper left of the periodic table, so it is one of the, it has only one valence electron. It gives it up very easily, and because it gives it up very easily, down here on the bottom, we'll try not to lose focus. Take that off. Lithium ion plus an electron to form lithium solid, 3.5 volt or 3.05 volts. There's nothing below this on this table. This is the most voltage you can get from any half reaction. So people have been trying to get lithium in batteries because of that fact. And if you turn it around the other way, we get a positive voltage. We always want a positive voltage. So the lithium-ion battery is this one. Lithium metal reacts to form lithium ions, and lithium ions react with cobalt dioxide to make lithium cobalt dioxide. And again, when you look at the overall reaction here, everything's a solid. They have a very long shelf life. You can recharge these. And because they use lithium, they're very lightweight, contrary to the feeling you get every time you pick up your computer. I mean, it's the battery that adds most of the weight to laptop computers. I'm sorry? How do you mean half the number of moles? Don't I have the equation balanced? I mean, total mass of what's in there, yeah, there's much less mass too in comparison to the other things. I mean, compare this to lead. Even if you add 1 mole of lead, I mean, it's huge weight difference. Those are the voltages. If you look on the back of your computer or you look on the back of your cell phone, it's got a lithium-ion battery in it, you'll see that it's about 3.5 volts. That's how much voltage you can generate. It's a huge amount of voltage. And you don't need a whole lot of current to get these to work. However, you also probably know these are exothermic reactions. How do you know they're exothermic? Use your laptop on your lap for a little while. It heats up. Talk on your cell phone for a few minutes. You can feel the heat coming off the battery. Okay? And so you feel the heat going out of these. But all that voltage is what you really want. Now, if you really wanted to get a lot of voltage, you'd somehow combine lithium with potassium. Actually, not lithium with potassium. If I could combine lithium with fluorine, so let's see. I'll pull that back in just a second. Lithium ions, or lithium metal. .05 volts. And fluorine. So if I could combine lithium with fluorine, these would be the 2 most reactive elements. I would have lithium solid, 2 of these, plus fluorine gas to form lithium ions, 2 of them, plus 2 fluoride ions, and I would generate 5.92 volts. And before you sit there and think, who'd be crazy enough to do that? If that's the maximum voltage we could ever get from chemical reactions, people are crazy enough to try to do this. And yeah, you're dealing with fluorine gas now. You can't store fluorine very easily. It's not good stuff. But there are people trying to do this to see if they can figure out a way to generate the power or the voltage they want. What kind of batteries are they going to use for cars? If you go to 42 volts and you put 3.5 lead storage batteries in there, you've just put more weight in the car, even though you've worked so hard to get weight out of it. One of the first prototypes were using just that. But now what they're doing is they're combining different kinds of batteries, because you only need the high current density when you start the car. So you have to have something with a high current. You're going to need one lead storage battery. But to generate the power needed to run the braking system and the steering system and the radio and the lights and everything else electrical in the car, and think about it too, compare cars today with cars 10 years ago. What's the big selling feature? Oh, they have DVD players and they have all kinds of GPS and navigation systems. All that stuff requires power. So they're going to put lighter batteries in them. There'll probably be lithium-ion batteries in there. There will probably be nickel-cadmium batteries in there. There will definitely be rechargeable batteries. And you'll have to have access to some of them because they'll also need to be replaced. They don't have an infinite life. Question?
Oh, I was just going to ask why you couldn't use the kind of batteries that we use in electronics like in a car.
You could use the kind of batteries we use in electronics in your car. And so that's part of what they'll do. The question will be, does it need to be a high current? If you need a high current, the batteries that we use in electronics now, in handheld electronics, does not need a high current. But to drive a DVD player, you need a little more voltage. You need a little more current. And so that's going to require it. If you're going to have a navigation system, that's just like you already have a navigation system in your handheld phones, right? So it's just like that. The other thing is, the car we bought, not recently, 4 years ago, has what, 6 plug-ins in it so that each one of the kids can be plugged in to the power supply at the same time? Okay, you sure? Okay. You have 3.7 volts on yours? It's a lithium-ion battery? You can read that. 3.7 volts, it says it's a gold lithium-ion battery. Does it say AU in front of it? Does it say? Oh, it's French, so it's with. All right. So if it's, well, see if you can figure out what the other half reaction is. You said the voltage on there is 3.7 volts. If the lithium generates 3.05 volts and the total voltage is 3.7, what does the other half reaction have to be? How many volts? 0.65. So we can work our way backwards, and we find out that here's a 0.68, which is oxygen plus hydrogen to make hydrogen peroxide. I hope there's not hydrogen peroxide in your iPod. There might be. This one, though, is permanganate with water to make manganese dioxide and hydroxide ions. That's possible. I doubt that it's iodine. It could be iron, or more likely silver. There's probably silver inside that as well, and so the silver is what the other half reaction is. Now the question is, and we'll answer this Friday, why is the voltage not exactly 3.05 plus 0.85? And so we'll talk about that on Friday. I'm sorry?